Good morning once again, and thank you for your time. I'm joining for this webinar on Let's Learn Simulation Training Series. So, hope you all know that we have been started this training series from last couple of months, and this is our fourth training session on Let's Learn Simulation. So today we will focus on model analysis, that is frequency-based analysis or frequency analysis, and we will also look into certain fundamentals of linear dynamic simulation. Okay, so I see people are yet joining. So yeah, we have enough number of attendees. So we will start with the session. So uh, I see people. The people who are new to this session, so who do not know me, myself, Shamil. So I work here as application engineer for simulation solution at Solid Dimension. So I am certified technical support for SolidWorks products and expert in SolidWorks simulation, structural simulation and flow simulation, and with respect to the Simulia Abacus. So in today's session, what we will see is we will see the training series recap, what we have done so far, what is the progression with respect to the training series. We will understand static and dynamic simulation concept, and we will also brief on the frequency analysis. So this analysis I'll be performing with respect to SolidWorks simulation. What are the key parameter you need to consider, as well as how do you interpret the results. And we will also see a brief on time history analysis, harmonic analysis, random vibration analysis. So these are basically the linear dynamics concept, and we will take one simple example on the engine frame support, and we will try to set up or how this setup can be done with respect to SolidWorks simulation as same setup in the 3D experience Abacus. And we will look onto the result interpretation part, and I have also added one session that is frequently asked question from SolidWorks user base. So what I have observed so far was with respect to the training series, we have got um, lot number of queries or questions or kind of suggestions how this can be improved and how this can be benefited for all of the engineers or all of the SolidWorks customer base. And I have tried to put up few questions or not more than two or three, and we will which is more generic towards all the audience. I will try to answer it in on live. And finally the Q&A session with respect to any SolidWorks simulation or any physics simulation part, or with respect to the session what we are going to do today, right? So let's learn simulation training series. Why we have started all as I already discussed. So the engineering knowledge with respect to the CAD design and same engineer to perform the simulation. It most of the industries are requiring that, right? So the person or the engineer who is going to do the design, he should be having the knowledge on the simulation or the virtual simulation tool, just to understand whatever the design he have done, it is pretty much enough in the real world condition. And innovation part or customization and personalization, and to meet up the standards and quality, right? So to keeping that in mind, we have introduced this training series. And as already know, so in the training series of this year, we have planned for fundamentals of FEA and CFD and basic level knowledge and tool introduction. And the next year, as a continuation of this training series, we will be taking up the advanced or intermediate to advanced application, focusing on various physics simulation, right? So the training series which is happening, so which has happened so far, is predominantly on the fundamentals and understanding the tool aspects. And this is the progress I could tell. So we have, this is our fourth session, and we have completed the static simulation of a pump assembly, how to do a assembly level simulation in SolidWorks as well as 3D Experience Abacus. And we have also completed the buckling analysis of a simple stool assembly. What are the key parameters you have to consider? And the last session was on structural thermal simulation. So all these training series videos or the session recordings has been published in the YouTube as well. And I believe these recordings has been reached to you all of. So one more suggestion, try to attend in the online itself if it is more you have more schedule with respect to your projects or the work. At that time you can go with the recordings, and whatever the questions or the queries you have, you can just put up in the live chat. So understanding static and dynamic simulation. So far we have done predominantly on the static simulation part, and today I will be introducing the dynamic simulation. So just an example wise, we have a engine with it has a block, right, where it is supported. So this is how we do the CAD design, and eventually we will do certain simplification in order to run the simulation, and we do the simulation setup by giving the boundary condition or self weight of the engine. So what are the expected results what we get here, right? So the static simulation stresses and displacement. So when I talk on this static, there are certain assumptions we do with respect to the static simulation, right? So the first assumption could be response is proportional to the applied load, means if the applied load is increased by 2 times, your displacement is going to increase by 2 times. This is what known as linear, right? So linear static analysis. When this is not proportional, it will come to the non-linear analysis. It might be with respect to large displacement or sliding or contact kind of thing, right? Or with respect to the material as well, right? So this is one assumption we consider. And yes, material is linear elastic. And this is the key assumption what we do with the static linear static analysis, that is loads are static, right? So loads are applied slowly and gradually, right? So if I just show in my paint, just let me take, just assume like I have very simply a cantilever beam, right? If I am performing a linear static analysis for applied load F, so if you are performing a linear static analysis, these loads are very slowly and gradually applied in order to have a equilibrium of this entire system. So this, whenever you perform a linear static analysis, the load is constant, or rather than telling constant, I can tell like the load is not varying with respect to time. So it is a static load, right? So this is one assumption we'll be also doing while performing a linear static analysis. Once the analysis is performed, we will try to evaluate what are the stresses developed because of that static behavior, and we will also see because of its self weight and because of the real world condition, it might be the applied load, right, how the displacement is going to happen. And finally the engineer is going to evaluate the factor of safety. Finally, the engineer is going to evaluate the factor of safety, how safe the design what I have done, and what is the factor of safety, whether it is over designed. If it is over designed, what you will be doing in the same environment, you will be changing certain dimension might be, or the geometry it might be, or with respect to the material, and then you will be rerun the simulation to get the more optimized solution, right? And we will also see certain connector plots. Connector, when I say connector, it might be your bolts, welds, springs, bearings, all sort of things. So when it is assembly, you get all this coming into picture, right? So in the static analysis, these are the parameter you evaluate, and you start doing the optimization of your simulation, right? And when it comes to the governing equation, you can see K into U, where K is the stiffness matrix, U is the displacement, and force. So this is the governing equation what we use for linear static simulation. So just quickly, if I come to the governing equation, so I have m into x double dot, which is my acceleration. This is my damping factor into velocity plus stiffness into my displacement is equal to f of t. So when it comes to the linear static analysis, the inertia part and the damping part or the velocity and acceleration is neglected and it is zero, right? And the stiffness is the with respect to the boundary condition and the material, and this f of t is constant. It is not varying with respect to time. So basically at the end, your static simulation governing equation becomes kx is equal to f, where x is my unknown, where the simulation software is going to give you unknowns, right? So when it comes to dynamic simulation, right? So we will be doing the dynamic setup, and the first key part is the natural frequency, right? So I will come to natural frequency. What exactly is natural frequency? Why it is important to evaluate your model analysis or different modes and frequency with respect to the assembly level. And once the frequency analysis is performed, we will also might do the time history analysis or harmonic analysis. So in detail, I will be explaining what is frequency analysis, what is time history analysis or harmonic analysis, just to give what might be the input and output for your dynamic simulation part. So natural frequency analysis is the fundamental for any dynamic simulation. And here the governing equation, uh, we are not neglecting anything. So we are going to consider the inertia, the energy absorption, which is basically the damping effect, and k into u or x, which is my stiffness into displacement, and f of t. And the main input with respect to the dynamic simulation, the force, whatever the applied force, right? With respect to linear static analysis, I told like it is constant and it is gradually applied. But when it comes to the dynamic behavior, because in the real world, nothing is static, right? Everything is going to operate. So either this applied load, it might be with respect to the time. For example, the shock kind of test or impulsive or impact kind of test, where the load is now with respect to time. So the load magnitude is going to change with respect to time. That is where when you perform this time history analysis, or the load might be with respect to the frequency analysis, where your random vibration or the harmonic analysis coming into picture. I will explain in detail in the coming slide. And what are the key outputs we look at from out of the dynamic simulation is the mode shape, right? Because of its own stiffness and material, how the mode shapes are, what are the frequencies, and we will also evaluate the maximum stresses and displacement over the dynamic event. So in static analysis, just at particular instant, what is the stress displacement we are going to evaluate. In dynamic simulation, during this dynamic event, what are the stresses developed or what are the displacement developed across this time step or frequency domain, and you are going to evaluate that maximum stresses and displacement. And you will be also validating the shock and impulsive effect, acceleration it might be, or velocity with respect to the vibration event and many more, right? So we will see how in detail each case, right? So what is frequency analysis or model analysis? So this analysis, as you all know, dynamic simulation, it is very vast. You have too many physics coming into picture, right? So considering the time, so today I will be performing only the model analysis or frequency analysis, what output you have to consider. And in the advanced training series, we will try to perform one harmonic or time history analysis. So when it comes to frequency analysis, why it is important for frequency analysis? So every structure has a tendency to vibrate at its own frequency called as natural or resonant frequency, right? So each natural frequency will be having its own shape. Or so when I come to, if I just put up the formula for the frequency analysis, so if it is my natural frequency is equal to 1 by 2 pi of square root of k by m. So this is my natural frequency formula, right? So what is the key factor here? This k, which is my stiffness, and this is my mass. So here there is no, in the natural frequency, there is no loading condition because of its own weight or because of its own stiffness, right? The system is going to vibrate in its own frequency, right? So during this dynamic event, that's what I was telling, for any dynamic simulation, it is very important to evaluate the frequency of a structure, right? So as I told, when a structure is properly excited by the dynamic load with the frequency that coincides, the natural frequency, the structures goes in. So what happens is, for example, my natural frequency is somewhere around 30 hertz, and your operating frequency is between 0 to 100 hertz. Just an example, what happens is there is a chance of getting a more stresses and displacement at this particular natural frequency, right? Which is called as my resonant. So at the resonant frequency, there is a chance of getting a high stresses sign, displacement or strain. So this is very important to evaluate during the dynamic event. That is why this frequency analysis, once you perform, you will understand what is the mode shape of each natural frequency, and you will see whether any frequency is coming between my operating design. So if you design a subjective to the dynamic event, static study cannot. Yes, static study is not going to consider all this effect. During the static point, what is the maximum displacement and strain you are going to get? So what are the key results? So this I will be performing very shortly. The natural frequency, the each mode shape, and the how the mass participation factor. Again, this I during the analysis I will be showing what to be done. Okay. So frequency analysis calculate the resonant frequency and corresponding mode shape, as I told, and linear dynamic study uses this information to calculate the dynamic response. So for any dynamic simulation, the base fundamental analysis what you have to perform is frequency analysis without any loading condition, how the structure is going to behave, that you need to evaluate before any dynamic simulation. So coming to the dynamic event called as time history analysis. So use model time history analysis when variation of each load is with respect to time, right? So as the name suggests, time history analysis, when your loading condition is with respect to time, at that time you have to perform a first static analysis to make sure for the maximum static load whether your model is safe or not. Once you perform that, then will be going for the frequency analysis without any loading condition, what is the excitation, then you will put the dynamic load to see the maximum stress assigned displacement, right? So what are the typical inputs for this analysis? It might be the standard test data what you have, or whatever the time load, whatever you have the data set, right? Straight away you can input it in the software, which you can see at this. So this is your input time curve, right? So you can see the time curve can be inputted here. So this is the loading case, and you can see variation with respect to time, and you will be inputting the time curve. So after running this study, you will be getting the displacement, you will be getting the stresses, strains, reaction force at different time plot, or different across your dynamic event, and this will specifically, or this will significantly help you to evaluate across the dynamic event how my model is going to behave, rather than just considering in the static event. So typical loading condition, as I told, it might be shock or pulse load, or general time varying load, right? And uniform base excitation with respect to the displacement, velocity and acceleration. So these are your typical loading condition. If you have this loading condition, straight away you can put up in your dynamic event, and you can see the highest stresses and displacement across the time duration. Next guy is the harmonic analysis, right? So as the name suggests, harmonic analysis is a frequency based analysis, right? So although what happens is, when you perform a time history analysis, right? So when you perform a time history analysis, you will be telling the starting time and end time. For example, let me tell 1 second. So what is going to happen across this time duration you are going to perform, right? So when it comes to harmonic analysis, you need not to perform entire time step. If you know once you perform a frequency analysis, you will understand, yes, my frequency first mode is 30 hertz, my second mode is somewhere around 60 hertz, and my third natural frequency is somewhere around 200 hertz. And your operating frequency, you can see this lowest and highest, right? If you know the operating frequency and your operating frequency is from 0 to 100 hertz, it is very important to see how your model or the dynamic event is going to, or what stresses are developed at this 30 and 60 years, because these frequencies might be play as a resonating frequency. Just an example wise, I have a frame which support this generator, right? So this generator is rotating. So operating frequency of this generator is from, just an assumption, like 0 to 100 hertz. So I will be performing a frequency analysis and I'll be getting all the first natural frequency, the first 10 modes, and then I will be performing the harmonic analysis. You can see 30 is my first node and 30 comes here. You can see the stresses or amplitude displacement very peak at this location, right? So wherever your natural frequency, so basically this 30 hertz is my resonating frequency. At this resonating frequency, you will understand, yes, this is my resonating frequency. From the software point of view, you can evaluate what are the maximum stresses, what are the displacement, whether my model is failing during the dynamic event. So this is how you perform a harmonic analysis. So to perform a harmonic analysis, first you perform a static analysis, then you make sure that your model is safe, then you will perform a frequency analysis to understand major. I will also show how many frequency you have to take for any dynamic simulation when I do in the software. Once you take out the natural frequencies, right, then either you will be performing a time history analysis if it is a shock load impact kind of thing, or during the transportation there is an acceleration happening, right? So these kind of inputs you can give load with respect to time. That is a time history analysis. If you have the operating frequency, you can straight away perform a harmonic analysis for the loading condition, and you will see across these frequencies where the highest stresses and amplitudes are going to come. And again, dynamic simulation, it is not straight as static simulation. So whatever the queries comes, please put up in the Q&A session. I'll be answering at the end of the session. So random vibration, again, this is one more event, which is one more dynamic event. So here the responses are deterministic loads, right? For example, one example I could tell, like the wheel of the car traveling on a rough road. We do not know how the loading conditions are, right? Or the base acceleration due to the earthquake event, right? So these kind of undeterministic load or non-deterministic load can be evaluated with respect to the random vibration. So what are typical input for your random vibration? So typical input for random vibration will be based on the standards. So for example, you have designed a modular, and this modular is going to ship it over, right? So during this event, there is a vibration happening. So you will be getting from the standard data set the PSD curve, the power spectral density. This will be the input for the software. So once you give the power spectral density and perform a random vibration simulation, you will try to get the probability of the stresses, displacement, strain across this dynamic event. Based on that, you can remodify or reconfigure your model. So this is just a brief on various dynamic event. Okay, so during the advanced simulation training series, I'll be taking up this concept and running. Today we will be see how natural frequency we can run, what are the output we will be evaluating. So we will see uh, um, in SolidWorks simulation how we can perform a model analysis. So I have an engine frame supported by a heavy engine as shown in this image. image. So we will analyze the frame to determine if there is any resonant frequency within the speed range of the engine. So let me assume like my speed range of the engine is from 1000 to some 12,000 or 15,000. So I need to check whether any frequency of this base is coming coinciding with this speed so that I can avoid the resonance. So let me take you through that. So discard SolidWorks simulation. Let me open up the model. So performing a natural frequency is pretty much straightforward. So if you see this formula, which I was explaining, right? Natural frequency 1 by 2 pi root of k by m. There is no loading, right? So for to perform a natural frequency, you need not to have any loading condition. Just stiffness, that is basically your material property and your constraints where it is fixed. And the mass, again, it will come from the geometry, right? So I have this model. So to perform a frequency analysis, I will activate the simulation. I will go to the new study. I will just check in with frequency. Let it be frequency 4 test. Okay. So let me click OK. Right. So as I told, my objective was I have to see the frequency of this base to see avoid the resonance. The engine, I need not to see how the engine is vibrating or something. I'm more focused on this frame. But this, the mass of the engine and the inertia of the engine has to be considered during this dynamic event. So what I will do first thing is, let me apply the material. So it is alloy steel, so which is standard material. So from previously I told, if the material behavior is not proper, make sure you copy and customize the material. So once I apply this material, right? So you can see all the material is applied. So I have an engine block. So what I will do is I will right click on the engine. You have a beautiful option called as treat as remote mass. So I will click on remote mass. So this engine load are distributed or connected, sorry, this guy. Again, this option you have in the static as well, static analysis. So let me, so this engine load, so I'm going to treat this engine as a remote load. Once I click OK, you can see this is my center of mass. From there, the engine inertia and the mass is going to uh, place it over these four mounted bolt. And here you can see there is a space. So whatever the small connecting thing, I have assumed as negligible weight and I have just suppressed it. So once I have done, you can see remote mass is done. So component interaction, I will give as bonded. So wherever is touching, wherever the touching faces is there, it is purely bonded. Or else you can also define, basically here there will be bolt or a pin, right? You can also define the pin connectors from here by choosing these two faces, right? So in this study, I will just assume like every location wherever it is connected, it is purely bonded. Okay. So material property I have done, I have to fix it to understand the stiffness. So right click on this and I will go with the fixed geometry. So the real world condition, it is fixed here. It is fixed over here. And it is fixed over this face and it is fixed over this face. Yeah. So once I click OK, you can see I have fixed over. So as I told, K by M. So mass, stiffness, fixedness, everything is done. No need of applying the external load. So now the thing is, if I right click on the frequency analysis, I have a properties. So you can see number of frequencies. So if I give 100, it will calculate first 100 modes and first 100 natural frequency. If I calculate 5, it will give first 5. So what is the number of mode I have to define? This is always a confusion between most of them. So what is the natural frequency I have to extract? So the thing is, so let me write it down here. So if you are performing a harmonic event, you know the engine speed, the operating frequency. You can just, for example, my engine operating frequency is from, so RPM, I can convert it into the hertz. Let me assume like 0 to 2000 hertz is my operating frequency of my engine. You can only extract the natural frequency which comes between this. And if you are performing a time history analysis, you do not know how many modes or how many natural frequency I have to extract, right? So in that case, you can use the mass participation. So let me give it as 10. So first, as an assumption, I will just take out the first 10 natural frequency. I will click OK. No external load. Meshing, let me go with blended with bit finer. Okay, so it is meshing is happening on the other screen. Yeah, this guy. So meshing is done. You can see by defining the remote mass, the meshing has not been done and the calculation is also not going to happen on this engine. But this effect is going to consider it on this base frame. Okay, so let me run this simulation. I'm not sure how long it is going to take. So it is running on other screen. So you can see generating interaction data, writing the data. It will not hardly take 2 minutes, I believe. So any questions you have so far with respect to anything, please put up in the Q&A session. So what I have done is just I have applied the material property fixtures. I know this is the only input required for my frequency study, right? And I do not know, just assume like I do not know the operating frequency. So what I have done is just I have requested the software to give me the first 10 natural frequency and the modes. Let's wait for some more time. I think the mesh is too finer. Let's see whether it will give any results. Okay, what I will do, let me cancel. Yes. Okay. The mesh, create mesh. What I will do, I will just select all. I will make it as a draft quality. I'm not going to consider the Jacobians here. I'm just doing the draft quality. So meshing is running on the other screen. Okay. And this is my draft quality mesh. Let me try to run now. I hope this time it has to run. Yeah, it's solving. Yeah. So you can see first 10 modes I have got, right? So basically what are the result interpretation you are going to do, or what output you get from just by performing the frequency analysis, right? First thing is definitely the mode shape. So if I right click, if I animate, right? So we can see the first mode, which is having 129 hertz, right? How it is going to have the first mode of animation. Similarly, you will get the second mode of animation. So the thing is, what says these modes? What basically tells these modes, right? So what I will do, I will right click here. Let me list my resonant frequency. You can see my resonant frequency 129, 133, first 10 natural frequency I have extracted. Why only 10 it has given? Because in the software I have given only 10. So there might be one more question, how many natural frequency I can extract? So it all totally depend upon your mesh. So how many degrees of freedom DOF you have, that much natural frequency you can obtain it. So what I'm trying to tell is, if I go on the details, notes, right? So I have a tet mesh. So 79,000 into 3, this much degrees of freedom I has. So these many nodes I can take out. But the thing is, if you see my natural frequency, so you can see here it is 2800. So as you increase the nodes, it will keep on increasing. One thing is, very higher natural frequency, no system is going to operate. This is one thing. If you know the frequency range, operating frequency range, you can only extract those. Okay, this is one point. And one more point, what you can get from here is the list mass participation. So if you see on this point, right, how you can evaluate. So you can see my first frequency is 129, and you have in X direction mass participation is 6.6, and in Y direction and in Z direction it is pretty much lower. And if you try to animate this one, most of the mode shape is happening on the X direction. In the similar way, if you if you see the second resonating frequency or the third resonating frequency, right? Why I am pretty much worried about this 359. 359, because you can see the X direction mass participation is less, Z direction is pretty much less, but in the Y direction I have almost 96% of mass participation happening for this frequency. Why this is a major concern is, my engine is also mounted on this, and its engine weight is also in the direction of Y. So whenever you perform a harmonic analysis between the range of 0 to might be like 1000, right? You can also predict like there is a chance of getting a resonant at this 360 or 359 frequency. There is a chance of getting a higher stresses and higher displacement when you perform a harmonic analysis during this case. So this is how you can evaluate the frequency analysis results. Okay. If I see my mode shape 3, and if I try to animate, predominantly it will be in the Y direction. You can see, right? So the mode shape, it is predominantly on the Y direction, right? So this is how you can evaluate the natural frequency, whether that natural frequency is coinciding with the harmonic. If you want to pretty much or understand the stresses and strain, then what you will be doing, you will be performing the dynamic event harmonic analysis, because you know here engine speed, you can convert it into the frequencies, and you can tell like 0 to 2000 is my operating frequency, and you can evaluate the analysis. And one more key thing what I could show as well is, you have a defined frequency response graph. This will give more insight with respect to the natural frequency. So if you see, right, X is red, Y is green, and blue is Z. And the third mode, you can see the mass participation in the Y direction is too much, too much. This is also one way you can evaluate the mass participation, and which might be my resonating frequency. Okay. And you can come to the conclusion whether I need to perform, if you are performing a time history analysis, whether I need to take all these 10 modes. That can be evaluated by taking defined frequency resonance, cumulative mass participation. This is one more wonderful graph which will give the insight. So where is this? Oh no. Yeah. So you can see this is my frequency. This is my cumulative mass participation. So if you see at this, after this frequency, most of the mass participation is stable, and most of the participation is happening on the initial frequencies. And this is the major one, again, the third mode. right? This is the frequency 3 something, yes, 358, right? So again, you need not to worry about these frequencies because most mass participation is not happening or kind of it is stable. You need to worry about these frequencies which comes when you are performing. It might be random vibration, it might be harmonic analysis, or it might be your time history analysis. So this is how you have to do a result interpretation even without running a harmonic analysis or random vibration. Pretty much information you will be getting from the frequency analysis graph. So coming back to my presentation, so result interpretation part, you have the comparison tool as well. So what are the different modes, in which direction it is? So predominantly what I understand, you have to look for the natural frequency, and you look for cumulative mass participation just to confirm whether all the modes you have captured. You should also look to the mass participation in which mode major mass participation is happening. In my case, you were seeing like the third mode, right? 359. The major mass participation is happening in y direction. And why this was my concern was the engine load is also in the y direction. When the operation happens, there is a chance of getting a higher stress assigned displacement with respect to these frequencies. So these kind of event you can never predict with the static analysis. And I have seen certain customers when I ask for how do you evaluate this dynamic event, they perform a static analysis. For the safer side, they just do 2 times or 2.5 or 3 times of the static load to, and they do the design for 3 times of a static load, and then they will be pretty much sure, like, yes, in the dynamic event also the model is not going to fail, right? So uh, what is going to happen is you are just doing a over design which is not much necessary. If you have the frequency, or if you can validate the frequency and dynamic event, you can optimize your product and you can evaluate in a more efficient manner, I could tell, right? So this is the part on the natural frequency part. So quickly I will show how the same analysis, how quickly I have performed in the Abacus. Many of them are aware, right? With all new SolidWorks licensors, right, you are going to get the 3D Experience basic role, the cloud services for the maintaining the PLM solution, right? So if you want to perform, or if you want to perform just a static analysis or dynamic simulation or kind of a frequency analysis, you can now just purchase whichever the roles which will do your work. You can just add up this role to your platform and you can start perform. So let me show how easily you can perform in the 3D Experience. It will not take hardly 5-10 minutes. So I have this model right away from the SolidWorks environment. So you can see all my files are sitting in the task pane within the SolidWorks itself. So I will make sure where this is the credential in the 3D space where my files are going to sit. So save with option. So I am just going to save this entire model to my 3D Experience platform uh, just to perform my frequency analysis. So again, we have too many customers where they are started utilizing this 3D Experience platform just for the proper collaboration point of view. So once, if you are already implemented this 3D Experience with this cloud services, your model will be already inside the platform. You have to just choose which model you are going to perform the analysis right from the SolidWorks, right? In the Compass SRD, this is a role name, structural designer, which is a basic role. You can choose that. So once I choose this linear structural validation, my native application for Simulia Abacus is going to open. So let me give the title name as frequency analysis. So whatever analysis I perform in the SolidWorks, same thing I'm going to perform here. So frequency analysis of the frame. So whatever questions you have, please put up in the Q&A session. I'll be answering at the end. So here I will just right away choose frequencies, the analysis I'm going to perform. So you can see the model has been come to my Simuli application. So this is purely connected to your SolidWorks. Whatever you changes you make in the SolidWorks, automatically it will get updated here. Okay. Now just with the help of the assistant pane, what you see on the right side, you can just come from the top to bottom just to finish up your analysis. So mesh settings, I will go with the default. Based on the geometry, it has given some values. So I will just generate. You can see in the back end, it is generating the meshes, right? So once the meshing has been generated, so yes, I think only the engine block is left. Yeah, so once the meshing is generated, I know I need not to do the engine block. So in the contributing part, I will just eliminate the engine part, because again, I can just put it as a inertia mass. I will, we, visuality, I will change to the model. So material panel you have inside the Simuli application itself. I will just drag and drop the material. You have n number of ways to do this. I'm more feasible with doing drag and drop. Again, you have a feature manager tree where you can apply the material all together rather than dragging and dropping. Okay, you can see when I do the drag and drop, automatically it is coming here. So once this part is done, so the material first three is done, right? Now I will go to the next one. So in the contacts, I know everyone is touching. So just find the surface where automatically it will detect all the touching faces. Automatically it will detect all the touching faces. Just you give apply, the connections is also generated, right? So next I am going to the remote inertia. Here it is not a remote mass. Here this is called as a remote inertia. So I will choose wherever the body was fixed, right? So this location. Now I have to give these input mass, the inertia in XX, inertia here 1 refers to X, 2 refers to Y, 3 refers to Z. So IXX, IYY, IZZ. So how do I get this value? So go back to your SolidWorks, right? So this is my model. So let me open up. So in the, you can evaluate with respect to the evaluation tab, mass properties, right? You can see, I can see the weight of this model based on the material applied. It is approximately 47.5, and you can see at the final IXS value, IYY value, IZ. So these input you have to just put up in the platform. So I will just go back here. In SolidWorks, the option was straight away you defining the remote load, but in Abacus, the option is called as remote inertia, right? So just put up the location, and whatever the location I have specified here, you can see XYZ, that is the center of mass of that engine model. So pretty much whatever value I got from the SolidWorks mass property dialog box, I'm just going to define it here. So once I am done, yes, even that part is done. So here I don't think there's something to be done. Yes, boundary condition, the fixture, which is called as clamp in case of Abacus. So I will just choose these locations. So I will not focus on the post-processing part because I have already explained. I'm just showing the how the workflow with respect to the 3D experience Abacus. Let it be more familiar to you all. So once I go to the simulation, right? So this is where the advantage of the cloud computing comes. Since so cloud computing, so the tool itself, the structural designer tool itself will come with a default 4 core, means even though if your system is having 2 core, you will be having a access to the cloud with the role of 4. Okay, so 4 core you can give the access. Since I have token, I can increase it as well. You can go up to 144 core if you have kind of very non-linear kind of analysis or highly explicit simulation. So which I'll be doing in the advanced session. So once I click on the solver, you can see the Abacus IMP file is going to write here. So whatever you see here, right, this is the IMP file format. You can see whatever the inertia factor I have defined, all these files are reading in Abacus. Basically, this is Abacus solver in the platform. So once the simulation is done, you can see extracting the results. Yeah, so all these data files will give the mass participation value, all those stuffs you will be getting from the data files in Abacus. So in the result extraction, I'm not just focusing, just straight away the displacement, all those stuffs can be done, and you can see the animation as well. Okay, so this is how you perform the frequency analysis in 3D Experience Abacus, right? So I just wanted to tell, like, we have got too many suggestions and queries with respect to this training series and with respect to the tool, right? So whichever I felt like which is more into the general audience questions, I just put up two or three questions. Let's see what is the questions. So most of them know SolidWorks as a CAD tool, right? So when we tell as SolidWorks, it is a CAD. It is meant for CAD. So how accurate is SolidWorks simulation software with software versus other simulation tool, right? So I am pretty much confident that we can get the results within 2% of an ideal structural analysis case. So the question is, how do I know? How do I know? So probably in 1983, there was an agency called as National Association for Finite Element Method and Standard, also called as NAFEMS. Okay, so to promote the safety and reliability use of any FEA software. So whatever the FEA tool you see in the market, right? So these tool needs to be evaluated by this agency, right? So they have set of benchmark model that all the simulation tool has to undergo in order to validate the accuracy, right? So again, we have also have you customers can also access the customer stories, might be pretty much similar application. You can just type SolidWorks customer story, and you can, this is an open website where you can get global level customer stories with respect to simulation, it might be, or with respect to any portfolio from Dassault System. So again, where do I get this validation report? I will also just show that. So if I go to the question mark in the SolidWorks simulation, even SolidWorks flow simulation is also having the validation report. You can see validation, NAFEMS benchmark, right? So it has opened in the other screen. Let me pull up here, right? This guy, you can see, right? So for example, if I take this cylinder, you have the theoretical value and with respect to SolidWorks what you have, and you can click here. So the model is going to open in SolidWorks. You can do the theoretical value or calculation what you have or whatever with respect to this, and you can evaluate as well. So just to for the information, so any tool in the industry has to go this benchmarking, even whatever the 3D experience Abacus we told, right? So even in the user guide of Abacus, you will be getting plenty of validation report benchmarks that has been performed with respect to the Abacus, right? So the next question could be, how is simulation tool going to bring return of investment even if our products are more efficient? Yes. So from couple of months, customers where we have been interacting, so they had all they have always had this concern, right? So how the simulation tool is going to benefit, because we are pretty much confident on the product whatever we are currently having, we are pretty much confident. So first thing I could tell, like lowering prototyping cost. So by performing simulation in virtual environment, definitely you can reduce the physical product, because any of the product, there will be certain standards that has to meet. Either you have to go for a virtual testing or prototyping testing. The prototyping testing, it will be costly, again it is time consuming, again if any changes to be done, right, the prototype model is waste or eliminated, you have to go for a new one, right? So this is one thing. And again, improving the quality, and I could tell it, yes, improving the quality, even if your products are already efficient, right? So simulation still can further optimize where uh, simulation can further do the optimization, right? So what I believe is, whatever it might, not with respect to simulation only, it might be any design, it might be, or any process workflow, it might be, right? wherever you put up your hand, there will be a scope of optimization, right? So there will be lots of ideas coming into picture. So how do you validate all your ideas, right? So you cannot keep on doing the prototyping, or you cannot keep on giving the outsourcing. So with the help of simulation tool, you can do the design exploration, where you will be doing iteration for different ideas, and this is how you will be bring value to your companies, right? And optimizing material usage, yes, definitely the previous point again, that optimization, it can drastically bring up the business. And again, optimizing the material usage, yes, simulation can identify the optimum balance material to be used. So what again I have observed, whenever I get kind of benchmarking kind of thing, when I do the testing, right, most of the customers are people who are doing the prototyping, or people who are not doing the any kind of testing, they always go for a over design. When I tell over design, the factor of safety, again, it not just two or three, most of the time it is more than 10 also. Means you are trying to do the design 10 times for the requirement, right? So when you have a simulation tool, you can eliminate all these factors, right? So this is again a more generic question which I listen from most of the customers which we have. And yes, why to choose SolidWorks simulation or 3D experience? Yes, again, whenever we have a discussion, because there are lots of tool in the market, right? So as a SolidWorks user, why to choose SolidWorks simulation or 3D experience Abacus, right? So one thing is fully integrated with the CAD modeling, right? So when I tell fully integrated, you have seen how 3D experience Abacus, or it might be Abacus desktop solution, or your SolidWorks simulation, right? So wherever you do the design, you will be performing an analysis, or with respect to 3D experience, you will just push. And always this virtual simulation, it is not just one iteration. If you want to do the changes, you come back to your CAD environment, right? You do the design changes, automatically the simulation is going to update, right? So when you do kind of some 10 iteration, the front end go back of that process is eliminated here, right? So no creation of simulation study, that is simulation will automatically update. So whatever modification you do on the CAD part, it will automatically update. And one more thing is, with SolidWorks and 3D experience, whatever the parameter you use in the sketch, right, this can be used for uh, driving your optimization. The simulation tool itself will tell what value of thickness, or what material you have to use with respect to the optimization. And yes, in case of engineers and analysts, one more key thing what usually they tell is, we have a issue with input. And so you can see the poll which I have, just for a reference I have kept. So when we had a webinar during the March or April time, so I just put up a poll called how difficulty is going back and forth between the CAD and simulation. You can see almost the 50% of audience, they were telling it is really painful or issue while importing exporting, right? So really painful, it might mean like you have done the simulation in the any third party software. Yes, it is, every software is good, gives the good accurate results, but the thing is, once you do the analysis, you have to do certain changes from that ideas, right? You will come back to the SolidWorks, you will do the changes. There is no communication between the SolidWorks and third party tool, right? So when it comes to 3D experience Abacus, or with respect to your SolidWorks simulation, these purely everything comes within the Dassault system portfolio. Everything can be communicated between each other, right? And issue while importing, exporting, yes, again, analysts used to tell, when we convert it into the step, or when we convert it into the any neutral file format, and then we open up in the other third-party tool, right? So other third-party tool might be sometimes the surfaces are missing, or kind of in the SolidWorks you have done a good mating, proper coincident mate, but when it comes to there is a chance of misaligning of this mate, right? What happens is, whenever you give the interaction property, right, that time again there will be a challenge. Again, you have to work on those part in the pre-processing, because simulation is pre-processing, solving, and post-processing. So pre-processing and post-processing, it is in the same tool itself. And definitely the cost point of view, yes, cost, when it comes to other industry standard tool, the cost of the SolidWorks simulation or with the Abacus 3D experience Abacus, I could tell, yes, it is much lesser compared to other tool, right? So this information I felt like just to give to in the general way. Okay, so next thing is value offering and announcement from Solid Dimension team. Yes, you are aware of whatever the offering we are providing. So you all know SolidWorks 2024 SP 3.1 has been released and now it is ready for upgradation. If anybody is still using the lower version, please feel free to contact. We can upgrade and make sure you are in the active subscription. Right. And we have also done the announcement of PDM implementation for SolidWorks professional and premium customers because customers has started telling the purely on the CAD point, the references issues, kind of managing the data or revisions, right? So again, my colleague Mr. Sampath has done a webinar on this, and this recording is also available in our YouTube channel. And the again, the announcement of 3D Experience Cloud Services for new SolidWorks license and implementation. So because you all, pretty of our customers know that with every SolidWorks license now you are going to get the 3D Experience roles, right? And based on whatever requirement you have, or we usually do the stage wise implementation, and we have started always we have already started with most of the customers. Again, we have doing this implementation with free of cost. And there are certain promotional offers going with respect to SolidWorks simulation and 3D Experience Abacus. So this offer pretty much from, I believe, from couple of months we are running this promotion. So simulation professional and premium with 25% of discount and free industry specific training, right? And flow simulation with the CFD part. Okay. So mostly so far we have done structural simulation training. From next 2-3 session it will be on the CFD analysis, understanding the flow parameter, thermal management, all sort of analysis I will be performing. Okay, so again in SolidWorks flow simulation you have 25% of discount and free industry specific training, and multi physics package you have for the structure and flow, and again there you have 30% discount and free industry specific training. And 3D Experience Simulation Abacus with embedded HPC, as I told, 3D Experience Abacus comes with the inbuilt cloud computing, right? So certain roles comes with 4 core of cloud computing, and there are roles which comes with 8 core of embedded. You need not to purchase this 8 core. With the software itself, you will get this 8 core and you have flat 10% discount on the yearly license for the Abacus. And very last announcement, SolidWorks CAD training on 10th September. Most probably you all will be receiving the invite link. Again, I can put up that link in the chat as well. You can do the registration now itself. I'll be just putting the chat. So it is on tips and tricks, SolidWorks CAD sketching. Okay. So I'm just stopping this webinar, and you will be receiving the CAD invitation. You will be receiving the recordings. The next session will be on the CFD, and there are certain announcements which we have made. So these are the key information I believe we could give as of now. And thank you for the time. Thank you for joining this training series. Your suggestions are welcome. If any suggestions, feedback, feel free to tell us. Thank you.